chill, but goes crazy every once in a while. I already gave her some exercise today, so she should be okay. And just as I say that, she starts barking. Yes, there you are, barking. Okay. So anyway, yeah, let's jump right into it. Syntax and semantics of Common Lisp. By the way, if there's anything about my setup that's not working, like if my audio is badly balanced or uh, deep fried like it was in the Bedrock video, please let me know in chat. I have it open here. Woof. Not you. I don't care about your opinions, Clips. Um, yeah. By the way, this music is I just searched out streaming copyright-free music and clicked on the second result because I've already used the first result. Welcome to the stream. Okay, jump right into it. Syntax and semantics. So last time we did a whole bunch of stuff and we went kind of a little bit too fast, maybe. So now he's gonna sit back. This book is by Peter Siebel, by the way. I don't think I had the name there last time, but yeah, that is the name of the author. Thank you so much, Peter Siebel. Mic is working, music isn't. Really? I'll turn it up then, I guess. Oh, now it isn't working at all. There you go. Okay, bye, Ryan. Don't worry, I'll probably still be here when you come back. If not, who knows? Yeah. Okay. Syntax and semantics. What is with all of the parentheses? What is the deal with parentheses? Lisp syntax is quite a bit different from the syntax of languages descended from Algol. Now, Algol, if you're not aware, is the predecessor to languages like C and, all Java and JavaScript and Go and Shell and all of those languages that have curly brackets. Basically, those are descended from Algol, and so they typically have like infix notation, curly braces. They abbreviate like type names and stuff like that. Lisp syntax is different from that, though. The two most immediately obvious characteristics are the extensive use of parentheses and prefix notation. For whatever reason, a lot of folks are put off by the syntax. Lisp's detractors tend to describe the syntax as weird and annoying. This is something that I've seen. I'm not sure whether I thought this or not going in. I probably did. Father, forgive me. Lisp, they say, must stand for lots of irritating, superfluous parentheses, which is dumb because that's not how acronyms work, but whatever. Lisp folks, on the other hand, tend to consider Lisp's syntax one of its great virtues. How is it that what's so off-putting to one group is a source of delight to another? I can't really make the complete case for Lisp's syntax until I've explained Lisp's macros a bit more thoroughly, but I can start with an historical tidbit that suggests it may be worth keeping an open mind. When John McCarthy first invented Lisp, he intended to implement a more Algol-like syntax which he called M-expressions. However, he never got around to it. He explained why not in his article, History of Lisp. The project of defining M expressions precisely and compiling them, or at least translating them into S expressions, was neither finalized nor explicitly abandoned. It just receded into the indefinite future, and a new generation of programmers who preferred S expressions to any Fortran-like or Algol-like notation that could be devised. In other words, the people who've actually used Lisp for over the past 45 years, that'd be like 50, 60 years now, have liked the syntax and have found that it makes the language more powerful. In the next few chapters, you'll begin to see why. I don't really have a lot to say about that. breaking open the black box. Now, black box is a terminology not all of us really care for. There are some uses of the term black box that are cliched. They're just inherently cliched, like for a airplane's flight data recorder, you shouldn't call it a black box, because first of all, it's not black, and second of all, like, that's the opposite of what black box means in the abstract as a metaphor. So clearly isn't based on the metaphor. Whatever, it's all a mess. Big old weird mess, and that doesn't matter because this use just means a thing that we don't understand what's in it yet, and it just kind of does stuff, and we can know what it does but not what's inside it. But we're going to open the black box, which means we're going to learn what's inside it. Before we take a look at the specifics of Lisp's syntax and semantics, it's worth taking a moment to look at how they're defined and how this differs from many other languages. In most programming languages, the language processor, whether they're an interpreter or a compiler, operates as a black box. You shove a sequence of characters representing the text of a program into the black box, and it, depending on whether it's an interpreter or a compiler, either executes the behaviors indicated or produces a compiled version of the program that will execute the behaviors when it's run. Inside the black box, of course, language processors are usually divided into subsystems that are each responsible for one part of the task of translating a program text into behavior or object code. Okay. A typical division is to split the processor into 3 phases, each of which feeds into the next. A lexical analyzer breaks up the stream of characters into tokens and feeds them to a parser that builds a tree representing the expressions in the program according to the language's grammar. This tree, the abstract syntax tree, is then fed into an evaluator that interprets or compiles it. Because the language processor is a black box, the data structures used by the processor, such as the tokens and abstract syntax trees, are of interest only to the language implementer. Yeah, I can't say that, like, you ever need to dig into, like, I was going to say you don't need to dig into how bash constructs a string, but, like, bash string quoting is all weird, so you kind of do, but only, like, to know how to work around it. But yeah, it's that kind of thing. Nobody cares how most languages actually do the interpreting. In Common Lisp, things are sliced up a bit differently, with consequences for both the implementer and for how the language is defined. Instead of a single black box that goes from text to program behavior in 1 steps, Common Lisp defines 2 black boxes, one that translates text into Lisp objects, and another that implements the semantics of the language in terms of those objects. The first box is called the reader, and the second is called the evaluator. What's my hands doing? I don't know. Oh well. By the way, I can't actually see my webcam down there. You see how the mouse just kind of disappears. I have something else there. It's like a little input method box, so I can type in Japanese, but it doesn't actually show what's that's an OBS overlay basically, whereas on my other system it was like a pop-up window. So that's why I can't see what I'm doing in real time. So I'm not sure if my camera is backwards or not. Whatever, it doesn't matter. So each black box here, each part of the Common Lisp interpreter defines 1 level of syntax. Level, okay. Not sure what they mean by that yet. Quite. The reader defines how strings of characters can be transmuted into Lisp objects called S-expressions. Okay. And there's a footnote, so we'll go down to the footnote. Where is footnote number 3? Sometimes the phrase S-expression refers to the textual representation, and sometimes to the objects that result from reading the textual representation. Usually either it's clear from context what is meant, or the distinction isn't that important. Okay. So yeah, S expressions usually have like parentheses around them or something. Since the S expression syntax includes syntax for lists of arbitrary objects, including other lists, S expressions can represent arbitrary tree expressions, much like the abstract syntax tree generated by the parsers for non-Lisp languages. Okay, so we already don't need like a separate parser and lexer, I guess. The reader just does both of those things because it combines the operations by the syntax just already being in the right form, I guess. The evaluator then just defines a syntax of Lisp forms that can be built out of S expressions. Not all S expressions are legal Lisp forms any more than all sequences of characters are legal S expressions. For instance, both list of foo 1 and 2 and list of quoted foo 1 and 2 are S expressions, but only the former, that's this first one there, can be a Lisp form since a list that starts with a string has no meaning as a Lisp form. Yeah, so let's actually just try this in the REPL real quick because I'm curious. Foo 1, 2. And of course, foo isn't defined, so that won't work. It's an unknown key argument. Okay. That's right, because we actually did define foo in the last episode. Now what happens if we quote foo? Execution of a form compiled with errors. Illegal function call. You can't just call a function that's a string, apparently. So that's all that means. The split of the black box has a couple of consequences. One is that you can use S expressions as an externalizable data format for data other than source code, such as our DB, which I've recreated on this computer slightly differently. I fixed the Japanese there, so it works now, except it doesn't, but it actually does, though. Anyway, you can use S expressions as a data format for data other than source code, using read to read it and print to print it. The other consequence is that since the semantics of the language are defined in terms of trees of objects rather than strings of characters, it's easier to generate code within the language than it would be if you had to generate code as text. Generating code completely from scratch is only marginally easier. Building up lists versus building up strings is about the same amount of work. I was going to say. The real win, however, is that you can generate code by manipulating existing data. This is the basis for Lisp's macros. There's macros again, which I'll discuss in much more detail in future chapters. For now, I'll focus on the two levels of syntax defined by Common Lisp: the syntax of S expressions understood by the reader, and the syntax of Lisp forms understood by the evaluator. So we're going to start off with S expressions. And I'm going to just pause for a moment here because the music stopped too. The basic elements of S expressions are lists and atoms. Lists are delimited by parentheses and can contain any number of whitespace separated elements. Atoms are everything else, anything that's not a list. The elements of lists are themselves S expressions, in other words, atoms or nested lists. Comments, which are shan't be evaled. It just returns no value because there was nothing there, same as if you just pressed enter on an empty line. But if I do this is just a string, cool, so it is, Desu. 123 is 123, okay. That's pretty much it. Since lists are syntactically so trivial, the only remaining syntactic rules you need to know are those governing the form of different kinds of atoms, which is just a part of a list that can't be broken down, I guess. In this section, I'll describe the rules for the most commonly used kinds of atoms: numbers, strings, and names. After that, I'll cover how S expressions composed of these elements can be evaluated as Lisp forms. Okay, that's the next section, though. Numbers are fairly straightforward. Any sequence of digits, possibly with a plus or minus sign, or a decimal point, or a slash, or with an exponent marker, is read as a number. For example, like we just saw, 123 is as 123. 3/7 with no spaces is the fraction 3/7, which I'm actually curious, what is that? What is 3/7? Okay, it just returns 3/7, I guess. That's just the way that they represent it. What if I do float? 3/7. Okay, apparently it's 0.428574143. Nasty. I can see why they just leave it as 3/7. That's pretty nice of them. Now, if you want to put a decimal point there and it keeps it as a floating point number, you can put an e at the end with a lowercase e plus an exponent value for like scientific notation style. If you put a d instead, that means double precision. If you put a negative number after e, that means it is a small number. Floating point equivalent to 1/10,000th. Okay. You can put a plus sign, and that just means it's a positive number, and a negative sign is a negative number. You can stack that with the fraction notation, of course. I just got a message, but I'm not going to answer it right now. Yeah. And if you write something like -2/8, it will reduce down to -1/4 because it's the same value. And if you write a fraction that has a value that has a whole number value, it will reduce to that whole number. These different forms represent different kinds of numbers. Lisp also supports complex numbers, with like imaginaries, which have their own notation. We'll discuss in chapter 10. I'm not looking forward to that. I don't like imaginary numbers much. Now, some of these examples suggest you can notate the same number in many ways, but regardless of how you write them, all rationals, integers, and ratios are represented internally in simplified form. In other words, the objects that represent -2/8 or 264/2 are not distinct from -1/4 and 123. Similarly, 1.0 and 1.0 times 10 to the 0 are just different ways of writing 1. But 1.0, 1.8, 1.0 with double precision and just 1 are different. They can denote different types of different objects because the different floating point representations and integers are different types. We'll save the details about the characteristics of different kinds of numbers for chapter 10. Okay, good. Okay, I want to not do numbers anymore. Let's do something else. Strings. String literals, as you saw in the previous chapter, are enclosed in double quotes. Within a string, a backslash escapes the next character, causing it to be included in the string, regardless of what it is. The only two characters that must be escaped within a string are double quotes and the backslash itself. Wait, so what is... Okay. So what if we format this particular string Oh dear. Okay, what if I... Cool. So okay, that works. So for example, the example they give in the book is less interesting. Just the string foo is foo. The string foo with the second O backslash is also just foo, because the backslash wasn't doing much of anything. But if you put two backslashes, one of them is real. That means that the first backslash escapes the second backslash. And if you were to put, say, a quotation mark there, now there is a quotation mark within the string, which is itself delimited by quotation marks. We can do that and it's fine. Names used in Lisp programs such as format and our little hello world function we made earlier, and the db variable, are represented by objects called symbols. The reader knows nothing about how a given name is going to be used, whether it's the name of a variable, function, or something else. It just reads a sequence of characters and builds an object to represent the name. Almost any character can appear in a name. Whitespace characters can't, though, because the elements of lists are separated by whitespace. Now I'm curious. Can we intern? Okay, maybe we can, maybe we can't. I don't know what intern does here. That's not what I thought it would do. Whitespace can't because the elements of list are separated by whitespaces. Digits can appear in names as long as the name as a whole can't be interpreted as a number. Let me get some Mountain Dew. I'm tired. Oh yeah. Okay. So if I were to yeah, that works. I can quote a thing that has a... That doesn't work. Okay, but I can quote a thing that has numbers, but not just numbers in it. Oh, but I can also just quote a number. Wait, is that the same as not quoting a number? I don't... What happens if I define 10? It does not work. Okay, we can actually make a function that's just a number. Cool. But we cannot make a function that is just a number. That's a little bit sad. I like functions that are numbers. Isn't that like the foundation of lambda calculus or something? Oh well. Similar names can contain periods, but the reader can't read a name that consists only of periods. Okay. 10 characters that serve other syntactic purposes can't appear in names. Here we go. Open and close parentheses. Okay. Double and single quotes. Sure. Backtick. That does something else. Comma. That also does something else. Colon. Oh. See, this is the difference with Common Lisp versus Emacs Lisp. eLisp, colons don't have any special meaning, but in Common Lisp they do. And that's how the package system works. Apparently, I haven't got to it, I never understood it. Oh well. Semicolon, because that's a comment. Backslash, because that's an escape. And the vertical bar. And even those characters can, if you're willing to escape them, by preceding the character to be escaped with a backslash, or by surrounding the part of the name containing characters that need escaping with vertical bars. I'm not sure quite what that means right now. Wait, so... Wait, okay, vertical bar... I hope they have some practical example of how that works. Two important characteristics of the way the reader translates names to symbol objects have to do with how it treats the case of letters in names, and how the case of letters in names, and how it ensures that the same name is always read as the same symbol. While reading names, the reader converts all unescaped characters in a name to their uppercase equivalents. Thus, the reader will read lowercase foo, foo with a capital F, and all caps foo as the same symbol. However, if you backslash all of the letters, like say I were to quote foo, that will be with all of them backslashed, or if I were to quote that escaped with vertical bars, that would do that as well, as opposed to just foo with quote, which is capitalized. Okay, cool. This is why you can define a function at the REPL and it prints the name of the function it's been converted to uppercase. A standard style these days is to write code in all lowercase and let the reader change names to uppercase. Cool. Because lowercase is just easier for everyone to write unless you're still stuck in 1970. To ensure that the same textual name is always read as the same symbol, the reader interns symbols. After it has read the name and converted it all to uppercase, the reader looks in a table called a package for an existing symbol with the same name. Wait, so a package is just a table then? We'll get to it. If it can't find one, it creates a new symbol and adds it to the table. Otherwise, it returns the symbol already in the table. Thus, anywhere the same name appears in an S expression, the same object will be used to represent it. That makes sense. We're not going to look at the footnote. It's going to be some exception that doesn't mean anything. Because names can contain more characters in Lisp than they can in Algol-derived languages like C, certain naming conventions are distinct to Lisp, such as the use of hyphenated names like hello-world, whereas Algol languages can only use underscores. Maybe. Another important convention is that global variables are given names that start and end with star. Similarly, constants are given names starting and ending in plus. And some programmers will name particularly low-level functions that start with names that start with percent or even double percent. The names defined in the language standard, that's Common Lisp itself, that's the one that all the implementations share, use only the alphabetic characters A through Z plus star, plus sign, hyphen, slash, 1, 2, the French quotes, equal sign, and the ampersand. Syntax for Lisp, strings, numbers, and symbols can describe a good percentage of Lisp programs. Other rules describe notation for literal vectors, individual characters, and arrays, which I'll cover when I talk about the associated data types in chapters 10 and 11. I'm familiar with the character data type from Emacs, so I'm curious. Apparently, that doesn't work the same way as it would in eLisp. Cool. Oh dear. Okay. Wait, what does it do there? Okay. Nice. Today I learned you can oh, that's not what that does. Okay. For now, the key thing to understand is how you can combine numbers, strings, and symbols with parentheses delimited lists to build as expressions representing arbitrary trees of objects. Simple examples like this. So we got, oh, hang on. So for example, you've got just like symbol X, you've got an empty list, which is nil. That's a cool function. Empty list is always nil. Nil means the empty list. That's what that is. You can also have like a list of numbers, a list of strings, which is just what it looks like, a list of symbols, a list of a symbol, a number, a string. That's fine too. And you can put lists inside other lists. This not... On my other computer, the mouse like follows the focus, but this one does not, so that's why I'm having struggle. That's why I'm struggling right now. But whatever. Here we are. As expressions as Lisp forms. After the reader has translated a bunch of text into S expressions, the S expressions can then be evaluated as Lisp code. Or some of them cannot. Not every expression that the reader can read can necessarily be evaluated as Lisp code. Common Lisp's evaluation rule defines a second level of syntax that determines which S expressions can be treated as Lisp forms. The syntactic rules at this level are quite simple. Any atom, any non-list or the empty list is a legal Lisp form, as is any list that has a symbol as its first element. Okay, so like function calls are fine, and just like non-lists are fine. Of course, the interesting thing about Lisp forms isn't their syntax, but how they're evaluated. For purposes of this discussion, you can think of the evaluator as a function that takes as an argument a syntactically well-formed Lisp form and returns a value which we can call the value of the form. Of course, when the evaluator is a compiler, this is a bit of simplification. In that case, the evaluator is given an expression and generates code that will compute the appropriate value when it's run. But this simplification lets me describe the semantics of Common Lisp in terms of how the different kinds of Lisp forms are evaluated by this notional function. Okay. So that's just a way you can think of it that might not actually be how it works. But it could be. You don't know. The simplest Lisp forms of atoms can be divided into two categories. There's symbols and there's everything else. A symbol evaluated as a form is considered the name of a variable and evaluates to the current value of the variable. I'll discuss in Chapter 6 how variables get their values in the first place. For example, you've got stuff like set q. So if we type foo, it'll return the value of the variable there. That's what that means. Should also note that certain variables are that old oxymoron of programming. They are constant variables. For instance, the symbol pi names a constant variable whose value is the best possible floating point representation to the mathematical concept pi. Look at that, 3.1415. Okay. Very cool. What happens if we try to set q pi to, like, I don't know, 3.15 or something? Error pi constant and thus cannot be set. Cool. Good for it, I guess. All other atoms that are not symbols, so to speak, stuff like numbers and strings, are self-evaluating objects. Means when such an expression is passed to the notional evaluation function, it's simply returned. We saw examples of this in Chapter 2 with like 10 and Hello World. We saw it earlier. That's all that was. It is also possible for symbols to be self-evaluating in the sense that the variables they name can be assigned the value of the symbol itself. Two important constants that are defined this way are t and nil, the canonical true and false values. Discuss their role as booleans in truth, falsehood, and equality, which is later, I guess. We'll get to it. For now, just know t is true, and nil is false, and the empty list is also nil, and not the empty list is true, because it's the opposite of false. Another class of self-evaluating symbols are the keyword symbols. Symbols whose names start with colon, keyword, stuff like that, and it just returns itself. When the reader inserts such a name, it automatically defines a constant variable with the name and the symbol as value. Excuse me, I am getting a phone call and I will need to end the stream briefly. I'll restart it just a second.